My name is Terry, and in this video we're going to learn how to execute a change of variables in a double integral, and then we're also going to talk about why it's sometimes beneficial to actually use the UV substitution and change the variables to evaluate a double integral. Right? So we have an example here on the board that we're going to use, and I'm pretty much going to show you how the process works with the given example. So our example, we're going to integrate 4x plus 8y, double integral dA. We're going to let the base be a parallelogram. Vertices are given for the parallelogram, and your xy substitution, the UV substitutions for the x's and the y's are given to you. Okay, so what we want to do is we want to take the integrand in terms of x and y. We have to adjust that so it's in terms of u's and v's instead of x, y. All right. Then we need to, for the new integrand, need to compute what's called the Jacobian. The Jacobian is going to be the determinant of your partial derivatives formed between the x's and y's and u's and v's. It's going to be a constant. It's going to be a variable, constant number that we're going to get when we compute the determinant of the partial derivatives. Okay, and then we have to deal with the bounds. We have to take the rectangle, the parallelogram. And we have to maneuver the bounds so the bounds of the parallelogram become in terms of u's and v's instead of x's and y's. So there's a process to get through. I have a 4-step process, usually the way I work them out and keep them in mind when I'm working through these problems. So when I'm working with change of variables with a double integral, the first thing I usually do, step 1 for me, is I compute the Jacobian. I get that and I write it down and leave it there. So I don't forget to include it in the new integrand. So for me, step 1, okay, so step 1 is to compute the Jacobian, right? So, all right, this is what I always do first, okay? So I'm going to compute the Jacobian first, okay? So the Jacobian, so I'm going to take the partial derivative in terms of x and y, okay? So I'm going to take the partial derivative of x and y in terms of u and v, okay? And I'm going to find the determinant of the partials, okay? So I want to take my x equation first in terms of u and v. I want to get the partial of u with respect to x first, okay? So that's going to give me, what, 1/4, all right? And then I want to get the partial with respect to v, okay? And that's going to give me 1/4, all right? And then I want to go to my y equation, all right? And I want to get the partial of y with respect to u first, okay? So partial of y with respect to u, and the u term's over here, so I'm going to need -3/4 for that, all right? So -3/4. Then I'm going to take my partial of y with respect to v. That gives me a 1/4, okay? All right, and so then when I go ahead and compute my my determinant here, I'm going to have the 1/4 times the 1/4, all right, minus the 1/4 times the -3/4, okay? So this times this minus this times this. It gives me 1/16 minus 3, minus a negative, so plus 3/16, okay? So that's going to be 4/16, which is 1/4, all right? So there's my Jacobian, all right? So this is what I'm going to need at the, so here is my Jacobian, and this is what I'm going to need for when I change my variables over to u's and v's, okay? So first I get my Jacobian, all right? Second step here for me, second thing I'm going to do is I'm going to change the variables in the integrand, okay? So I'm going to go ahead and take the integrand, which is 4x plus 8y. We're going to change the variables with respect to the integrand. So we step back over here. So step 2. So step 2, let's go ahead and change the integrand. So change the integrand over, okay? So the integrand right now in terms of x and y is 4x plus 8y. So this is what the integrand is, okay? So 4x plus 8y. Well, we want to change the integrand, which is in terms of x's and y's right now, to u's and v's. So you just make a substitution, okay? So let's go ahead and take the x and substitute in 1/4. X is 1/4 u plus v, okay? And then we have 8 times the y, and the y is 1/4. All right, and it's v minus 3u. All right, So when you compute this, the 4's cancel out, so you have u plus v here, okay? 1/4 of 8, that's going to be 2, so 2 times v, okay? So you have plus, okay? 2 times v, and then when you distribute the 2 over here, minus 6 times u, okay? So then what do we have when we combine this? We're going to have 3 v's, okay? Minus 5u, so 1u minus 6u, so minus 5u. This will be our new integrand when we rewrite our change of variables integral. All right, so far we're going to convert our integral, changing the variables. We're going to have a double integral. Our new integrand is going to be 3v minus 5u, okay? And then we're going to multiply by the Jacobian, will be 1/4, all right? So now we have to take care of the bounds, all right? Sometimes this is the busiest step, okay? So step 3, we need to adjust the bounds, okay? So step 3. Let's take care of the bounds. All right, so the bounds, okay, so let me move these steps out of the way. So we got step 1, step 2, so we got most of our integrands set. Now we're going to set up the bounds, all right? Now let's see, we have a parallelogram for our base. So let me plot these points, all right? So we have a parallelogram for our base in the xy plane. Here's the x-axis, here's the y-axis. We have a parallelogram, okay? So -1, 3, that's one of the vertices. I'll put it right about here, okay? So -1, 3, all right? Next vertex is 1, -3, so to the right 1, down 3. This is the next one, okay? So the right one, down 3. 3, -1, so to go to the right 3 and down 1 approximately. So I'm just approximating these 3, -1, and then to the right 1 and up 5, to the right 1 and up 5, okay? So this is what the bounds are right now. This is at 1, 5. All right. So this is what our base looks like right now. It's a parallelogram, so you can see both pairs of opposite sides parallel, and it's a parallelogram. All right. So to evaluate this double integral, we learned in a previous video that you have type 1 with vertical slices of a region, type 2 with horizontal slices of a region. If we went ahead and computed type 1 vertical slices, how many sets of double integrals would we need to set up and add together to compute this? Okay, so can you see that we would need to set up, because the vertical slices, if you put your slice here, it goes between this side and this side. Let me label the sides. I'm going to call this side A, I'll call this side B, side C, and side D. Okay, so if we tried to evaluate this double integral given the parallelogram, we would have to set up, let's see, if we did type 1 with vertical slices, this slice goes from side A to side B, okay? Move over a little bit, right here, if I put the slice here, it goes from side D to side B, and if I move it over to here, it goes from side D to side C. If I was to do a type 1 with vertical slices to get the volume of the solid, I would have to set up 3 sets of double integrals, evaluate 3 sets of double integrals, and add them together. That's a lot to do, okay? What if instead of a type 1 with the vertical slices, we considered a type 2 with horizontal slices? All right, so type 2 with horizontal slices, well, if you drew your rectangle way up here, it's going from side A to side C, okay? If you drew your rectangle down here, it's going from side A to side D. And then if you drew your rectangle, your horizontal slice way up here, okay, it would go from side B to side C. So again, to do type 2 with horizontal slices, you'd still have to set up 3 sets of double integrals, evaluate 3 sets, and add them together. Okay, so that's kind of a lot, kind of busy to do. So this problem does lend itself pretty well for the change of variables concepts, okay? Because when we change the variables, we'll be able to see that we can just solve one double integral, and it'll give us the answer that we're looking for, okay? Instead of having to do 3 sets of doubles this way or 3 sets of doubles that way and add them together. So we're going to go ahead and see how this works. So we want to go ahead and adjust our bounds, okay? We want to take these 4 sides, all right, because we have to change this to u's and v's. We have x's and y's, we change to u's and v's. How do we even begin that? They gave us a parallelogram and they only gave us the vertices. we have to take each of these four sides of the parallelogram and write them as a linear equation, okay? They're line segments, so we have to write side A as the equation of a line, side B is the equation of a line, side C is the equation of a line, side D is the equation of a line, okay? So we'll start with side A. All right, so side A, we want to write this as the equation of a line. So to write the equation of a line, we need to know what the slope is. So the slope, so 3 minus the negative 3, subtract the y coordinate, so 3 minus negative 3 over negative 1 minus 1, so negative 1 minus 1, so this gives you 6 over negative 2, so negative 3. Negative 3 for the slope, okay? And then pick one of the 2 points, okay? I'll pick this one, right? So y minus the y coordinate, okay, equals negative 3 for the slope quantity x minus the x coordinate is 1, okay? So we found the slope between these two, and so now when you compute this, y plus 3, okay, equals negative 3x plus 3. All right, subtract 3 from both sides, y equals negative 3x, and so here's your equation. Here's your equation for side A. The equation for side A is y equals negative 3x, okay? Then you have to go around and do that for side B, okay? And you need to do that for side C and side D. You need to compute this slope, okay? So compute the slope. All right, so what are the points here? So the points here are 1, 5, and negative 1, 3. So we want to compute the slope. So the slope 5 minus 3, so it's going to be 5 minus 3 over 1 minus a negative 1. So it's going to be 5 minus 3 is 2, 1 minus negative 1 is 2. This slope is 1. All right, and then when you write the equation, pick one of the 2 points, and you have y minus the y coordinate 5 equals your slope is 1, quantity x minus the x coordinate is 1. Okay, so when you compute the distribute the 1 and add 5 to both sides, you're going to have y equals, okay, so this one's going to transform over to y equals x. Let's see, it's minus 1 plus 5, so plus 4. Okay, so you need to write the equation of each of the 4 sides. What about side C? Okay, all right, what about side C? Okay, so I'm going to save all the computation. I'm going to just write down. So side C, well, opposite sides, this is a parallelogram, so you're going to have the same slope. When you find the slope and compute the y-intercept, you should be able to see that side C has the equation of y equals negative 3x plus 8. Okay, so I'll leave the computations for you to practice if you'd like, okay? And then side D. Okay, so side D, when you write the equation through side D, find the slope and write the equation of a line, you're going to see y equals x minus 4. Okay, so these are the equations of the 4 sides. Okay, so these are the equations, and so what do we have to do now that we have side A, B, C, and D of my parallelogram written as linear equations, y equals in terms of x? We now have to take all 4 of these and change these y's and x's over to u's and v's using our conversion scale. Okay, so we're going to change everything over to u's and v's. All right, so change to u's and v's. So let's start with side A. Side A was y equals negative 3x. Okay, so y equals negative 3x. Okay, so y equals a negative 3x. We're going to start with side A. All right, and what is y? I'm going to distribute. So y is 1/4 v minus 3/4 u. That's what y is, okay? Equals negative 3, okay, times x, which is 1/4. I'm going to distribute there also, okay? So negative 3/4, okay? So negative 3/4 times u minus 3/4 v, okay? So here's this equation, all right? And what can we do here? We can add 3/4 u to both sides, and they go away. When you add 3/4 u to both sides, they go away. Add 3/4 v to both sides, and you end up with v equals 0. Okay, so v equals 0. So here's our first equation that we need. We need equations in terms of u's and v's. Okay. All right, let's get our next one. So y equals x plus 4 is next. Okay, so let's take the side y equals x plus 4. All right. So y is going to be 1/4 v minus 3/4 u. When you multiply it out, x is what? 1/4 u plus 1/4 v. Okay, so 1/4 u plus 1/4 v plus 4. Okay, so what can we do here? Here we can subtract 1/4 v from both sides, and they're gone. When you subtract 1/4 u from both sides, you get negative u equals 4. So divide both sides by negative 1, so u equals a negative 4 for this side. So this one's going to be u equals a negative 4. Okay, here's what this conversion is. All right, so we have this. All right, the third side here we have negative 3x plus 8, so we have y equals a negative 3x, okay, plus 8, which is really this same equation here, but we're going to add 8 on to the end, okay? So I'm just going to it's the same thing, so it's going to be 1/4 v minus 3/4 u, okay, equals negative 3 times x gave us negative 3/4 u minus 3/4 v, and then we're adding 8 onto that, okay? So your 3/4 u, when you add those to both sides, go away. You end up with v equals 8 here, okay? So v equals 8 for this equation, all right? And then finally, y equals x minus 4. So y equals x minus 4, let's see what this brings us, okay? So y equals x minus 4, y is going to be 1/4 v minus 3/4 u, okay? Equals x is 1/4 u plus 1/4 v, and we want to subtract 4 here, okay? So the 1/4 v's will cancel when you subtract those out from both sides. When you subtract 1/4 u, you get negative u equals a negative 4, so this one's going to bring us u equals 4, okay? So u equals 4, so here's how we're going to take the sides of the parallelogram, write the equation in terms of x and y, use your conversions to change them to u's and v's, right? So now what does our uv, this is our region R, okay? So region R is the region that we have in the xy plane. This is our region R, okay? All right, so what's this going to look like when we set up region S? Region S is going to be the same idea in the UV plane, okay? So I'm just going to come over here. All right, I'm going to set up a U axis and a V. Instead of X and then Y, we're going to use U and V, okay? So what does a U and V look like? Well, let's see, U goes from negative 4 to positive 4, okay? So negative 4 to positive 4 for U. And then the v goes from 0 to 8, okay? All right, so you have negative 4 to positive 4 for the u-axis, and then 0 to 8, okay, for the v-axis. And so this is my S region, okay? So this is my S region, right? This is what I'm going to use, right? So do you see how much easier it is to use the rectangle instead of the parallelogram as our base? All right, remember the parallelogram, you would have had to set up 3 sets of doubles for a type 1 dy dx volume of the solid, or you would have had to set up 3 sets of doubles for the horizontal slices as well. So instead of 3 sets of doubles, look here, we'll just be able to 1 set of doubles. It doesn't matter if you go du dv or dv du, both ways, either way will work out fine. All right. So now we have our bounds set up, okay? So we have our bounds, and so finally, your final step here is just step 4 is putting it all together. So step 4, putting it all together or evaluate. Okay, so now you've got all the pieces. So I have this step-by-step process just so you can show you the pieces that you need for the integrand, okay? So we're going to put it all together and evaluate. So we're going to evaluate a double integral. All right, let's start with the integrand, okay? So the integrand, we need the integrand in terms of u and v. What is the integrand in terms of u and v? It's 3v minus 5u. So the integrand is 3v minus 5u. Okay, then what do we need? We need the Jacobian. The Jacobian comes next, and we want the absolute value of the Jacobian. In the event that your Jacobian comes out to be a negative number, make it positive, okay? So the absolute value, okay? And then you do need to decide, do you want du dv or dv du, okay? I mean, the screen, it does say du dv. In your book, we could do that, okay? So you want to do du first, okay? So what are the u bounds? The u bounds are negative 4 to 4. You can see it here, okay? And then dv, what are the v bounds? The v bounds are 0 to 8, okay? So there's your du dv, all right? And then we integrate from the inside to the outside, okay? So we'll carry the 0 to 8 with us, okay? And we're going to integrate. So I'm going to bring the 1/4, okay? We're going to integrate each term. We're going to integrate each term with respect to u. So this becomes 3 times u times v. We're integrating with respect to u, so v is a constant, okay? okay? Integrate with respect to u, so minus 5u squared over 2, okay? We're going to evaluate this from negative 4 to 4. We'll take care of the v afterwards, okay? So we have 0 to 8. All right, so we have the 1/4 out here, okay? Plug in the upper bound. Now we integrated with respect to u, so when you make your substitutions, the number goes in, 4 goes in for u, negative 4 and for u. So 3 times 4, so that gives us 12v here, minus, and then 4 squared, so that's going to be 16 times 5 is 80, and 80 divided by 2 is 40, okay? Minus, then plug in the lower bound. The lower bound, 3 times negative 4 times v, so that's a negative 12v. It's a negative 12v. And then you're going to plug in negative 4 and square it. So that's going to give you positive 16 again times 5. So 16 times 5 is 80, and 80 divided by 2 is 40 again. Okay? All right, so we have this. Let's simplify the integrand a little bit here. So 0 to 8. All right, what do we have? We have 12 v's minus a negative 12 v's. So 12v minus a negative, so you're adding the 12 v's together. 24 v's, taking a fourth of the 24 v's, okay? So that means we have 6v, okay? And then 40, negative 40, and then minus the negative, that makes a positive 40. So negative 40 and positive 40 is gone. So 6v, okay? So 6v, everything else went away and we simplified. So we're going to integrate this with respect to v. All right, so integrate 6 of v, you're going to get 6v squared over 2, so that's 3v squared. We want to evaluate this from 0 to 8. Okay, so you have 3 times 8 squared, okay, minus 3 times 0 squared. Okay, 8 squared is 64. 64 times 3 is 192. 192 would be your final answer. Okay, so 192. And this is change the variables, okay? So change the variables. So calculus 1, you'll do a u substitution sometimes when the integrand doesn't follow some of the rules that we've learned for integration, okay? So, but changing variables in calculus 3, there's many different applications for the change in variables. Most of the time, you're going to see the change in variables apply to just so you can move the base, so you don't have to set up 2, 3, 4 sets of double integrals to evaluate the volume of a solid, okay? So as you can see over here, it would have taken, if we left this in terms of x, we would have needed 3 sets of double integrals to evaluate, add together to achieve the volume of the solid, where we could just make the adjustment and change the variables using this process to make the final step a lot easier, much more easier to handle. Okay? All right, well, that concludes this video. Hope it helps with understanding the process of changing variables with double integration. Thank you for watching, and stay safe out there, stay healthy, and thank you again.